Okay, so I am going to, as predicted, talk about the SpiNNaker platform. I'll give you an introduction basically to what SpiNNaker is. So if this all works, it looks like it's going ahead. So first of all, I'll talk about what is SpiNNaker for those who don't know. So the idea of the SpiNNaker project, which started some time ago now, was to build a computer made of 1 million mobile phone processors. The idea of this is that it could simulate the model about 1% of the human brain, or in some people's eyes, 10 mice. So it's approximately in terms of numbers of neurons more than anything, not exact percentages or exact numbers of mice. Obviously, it depends on how complex the networks are and so on. This was sort of the aim of the project originally. So there are several application areas that we think SpiNNaker is applicable to. There is the neuroscience area, so we want to be able to use the platform to simulate brain areas, whole brain models, and things of that sort of nature in an attempt to better understand how the brain works. We're also interested in robotics, so the platform is actually designed to run neural network simulations in real time, and it has mechanisms which allow us to communicate with the outside world. So it's particularly well suited to running brains and control systems for robotic devices. And also we're interested in future computation. So the idea is learn from studying and simulating brains we could use to inform new computing devices and technologies, hopefully, and methodologies. So I'm not sure how much the audience knows about general computers. So here's a quick introduction to computer architecture, as might be found in a laptop or desktop computer. Usually you have a main central processing unit, which is clocked in the gigahertz, and it usually has a number of cores. 2 or 4 is fairly common on machines these days. The power is around about 35 watts for a laptop to 95 watts for a desktop, and servers quite often have a lot more cores and a lot higher consumption than this. The processor is usually connected to some external memory, which is measured again in gigabytes, and it's usually like 2 to 16 gigabytes in a laptop. Desktop, nowadays you're getting more like 32, 64, and then servers have a lot more. There's also usually a large storage device of some sort, more often now a SSD than a hard disk, but some sort of large storage where you can store things when the machine is powered off. And usually you connect the computer to a communication device of some sort to talk with the outside world or other computers. To go a bit deeper into the processor itself, there's usually some cache memory, which is fast memory that allows you to access the main memory and allows it to do computation. So this is maintained automatically normally, so the programs executed don't really see it, they just think about things being in memory. There's also usually something called the direct memory access controller. So this performs transfer of data between the processor and external memory. It can happen in parallel, so things can be going on while the processor is doing other work. Traditional computers are then often formed into networks of computers. So you get a network or a cluster, and they can then group together to do lots of things, to do different parts of the problem at the same time to get more tasks done quickly. The network infrastructure itself that connects these computers can also run in hundreds of watts. So to have a look at the SpiNNaker chip and see how this compares, this is the outside of a SpiNNaker chip. You can see it if you have a SpiNNaker board, you can look on top of it and this is what you'll see. But just underneath this, we've actually got the memory, the SD RAM, of which there's only 128 megabytes compared to the gigabytes that you find in the traditional architecture. This is also quite slow to access for the process of SpiNNaker as it is on a traditional computer, so it has to do work to get to this memory. Underneath this, we've got the connection, the actual main part of the chip, and there's a connection here that lets the cores of the chip speak to that SD RAM. There are 18 ARM 968 cores, which are 200 megahertz cores, and sometimes there's only actually 17 of these on the chip. It depends on the manufacturing process, basically. Sometimes we lose a core, and to make sure that we get enough chips, we allow that to happen. Each of these cores has 32 kilobytes of instruction memory where the programs are executed, and 64 kilobytes of data memory, which is pretty small in modern terms. This is similar to something like a BBC microcomputer more than anything than you would see in a modern world computer. The data memory is very fast to access, like the cache memory, but it isn't actually a cache. The program running on the core controls what goes into that memory, and the memory is very local to the core, so other cores can't access this either. It's completely isolated from the other cores. So the SD-RAM has to be used if you're doing any shared work. The processors also have a DMA controller, similar to a normal system, so you can actually fetch things from the SD-RAM in parallel while you get on with other things. But again, this is the control of the program, so you can do it whenever you want to as the programmer. There is a small amount of shared faster RAM, so it's more local to the chip. You don't have to go all the way to SD-RAM, but it's pretty small, so it's useful for system functions more than anything else. And we use it for message passing more than anything. There is an Ethernet controller embedded on the chip, so this is not external again to the device. Every chip actually has this, but there's actually only one on each board connected. I'll show you that in a bit. One of the big parts of SpiNNaker is this hardware router. This is quite different to a router found in traditional networks, and I'll show you how that works as well in a minute. Sorry, I'll go back to that. The whole chip and almost all the component has almost all the components to create a network of chips, so it's all inside it. The board does consume some power, but actually a single chip consumes about a single watt of power to do all that. So although the cores are slow, there's a lot of them, and it still only consumes a watt of power. So that's quite useful. So compared to your 35 to 95 watts in a traditional CPU, pretty good. So to go into more details of how this router bit works in the middle, the router architecture basically allows you to send to multiple destinations on a SpiNNaker machine. Here we want to send a packet from this red circled place called 11 on the board, and we want to send it to some cores that are on some other chips on the board, say 6.3, 6.4, and then there's some that are on different boards as well that we've connected together, and this is 8.3 as well. So when we send a packet, we can send a packet to the next chip, so we send it to 2.1, so we direct it there. Now, one of the features of the router is that if there's no entry for a packet on this chip that matches, then it allows the traffic to go straight through. So it means although we've only got 1,024 entries, we can actually get to 4.1 from 1.1 without any entries on the intermediate chips, which is quite useful. Now there, if we want to turn a corner, we then have to have an entry that says send it to the 5.2 chip, so it goes there, and again we can get to 6.3 then without anything on 5.2. Now when we get to 6.3, we actually want to send it to multiple places, and we can actually do this simultaneously in a single step. And then we can do the same sort of things from those branches. But actually that branching is part of the multicast, so that's done instantaneously, a single step. You don't have to have multiple entries for that. And then this way you get sort of multicast communication across the machine. The chips that we have are normally distributed on SpiNNaker boards. We rarely let people use individual chips, although it is possible. Each board then has an Ethernet connection, and the larger boards actually have two. And the second of these connections is for board management functions. So this allows us to control the boards and configure the FPGAs on the board as well directly without actually having to go through the SpiNNaker chips themselves. The boards then also expose a number of different ways to connect to external devices. So here we've got some external device ports, as I've called them, which are useful for robotic applications. And you can also connect to the FPGA devices down the side as well, but I'll go into more detail of that in a minute. So we wire these boards together to make larger machines. So a board has 48 chips on it, but we actually, a large board here has 48 chips on it, but we can wire those together to make even bigger machines. And so we connect them up something like this. We connect the FPGAs at the border of the chips. Note that not all chips are present in this machine. I'll come to that in a minute. So if we draw a diagram of what this machine actually looks like, it looks like this, and we can see there are some sort of gaps in this machine, and I'll show you why that comes in a minute. But basically, we formed a 16 by 16 machine with holes by connecting it up with connections like that. Now, if we actually connect all the links together like this, we can actually fill in those gaps. So it's a complicated arrangement, don't worry too much about the funny arrows. But basically these colors correspond to how these boards connect together. And what happens is it wraps around the network. And what you end up with is a set of boards that are connected together in a torus arrangement. So if you notice the spinning thing I had at the start of this simulation, that was a torus, and it's kind of connected that way to shorten the distance between any two chips on the system. So now the hexagonal arrangement of boards, of course, makes more sense because this is how it fills in the gaps. It's basically because there's this strange hexagonal shape is because you want to be able to fill in the gaps when you wrap them around. So we can actually then use the same process to build even more complicated machines where we connect those links together in more complicated ways that I will not get into the details of here. So if we connect 24 boards together, we get a machine that looks like this, and we do have one of these at least in operation at this point. But we can actually then connect 5 of those cabinets together in an even more complicated jumble of wires, as you can see here, to create a 120 board cabinet. And even better than that, we can connect 1,200 boards together to make our very big SpiNNaker machine, which we're running in Manchester. There's a animation here that shows you us booting the machine. Basically, this is how the machine boots up. It's loading all these chips. They all communicate with each other, and we're counting the cores as it goes. And you can see after the final boot, it's not live. That's to tell you we didn't do it live when we did this. Then it boots to over 1 million cores. Now, because the boards are so tightly packed together like this, we do have to have a cooling system in place for this. So technically, although the boards don't use much power by themselves, all these boards so tightly packed together do. And all the system with those 1 million cores and the cooling system uses about 100 kilowatts of power, which is still considerably less than a system built with traditional computers of the same sort of scale. So we've got this very large machine, but we don't actually want to let one user use that whole machine at any one time. We're lucky enough that one of our students wrote an allocation system that lets us partition that machine up into chunks. So the user job will ask a client, have a client in it, which asks the server to make an allocation of a number of boards. Once this allocation has been done, the user can actually access those boards directly now in the machine. To give you a little bit more detail, what happens here is that the server, when it's asked, configures the FPGAs of the board using the second board connection and actually isolates boards, or one board or several boards, from the rest of the system completely. Now, this means if you somehow mess up or somehow the software doesn't quite do things correctly, it means that these anything that's sent out on the networking of this board is isolated from the other boards, which means you can't accidentally get spikes from a separate job. As I say, when the user's actually accessing it, then they're accessing the Ethernet ports of these boards that they've been allocated directly. So you access that from wherever. Now, our network is actually isolated from the world. So we have that machine room where I showed you the picture of the SpiNNaker machine is actually isolated from the world, but our servers in that machine room let you run your jobs on there. But of course, you've still got the allocation process going on, and anyone that's in Manchester can actually access the machine a bit more directly. So the allocation process means that jobs are not treading on each other's toes, basically. So once we've got all that hardware, we also need some software to make it easier for users to use it, because it's a fairly complicated system in itself. So what we have is a software stack which consists of 2 halves, where the communication is done over the Ethernet with the SpiNNaker chip. So that we have a host side, which is usually a server in Manchester that does this, but if you're lucky enough to have your own SpiNNaker board, it might be your own laptop that does this. I have one sitting on my desk that you can't see, but it is sitting down there. So on the SpiNNaker side, we have a low-level hardware API, which lets us communicate directly with the SpiNNaker hardware. On top of this, we actually have a chip monitor software. Basically, what we do is when we boot the machine, we load the monitor software onto one of the cores on each chip, which allows everything to communicate then with each other and the host to communicate with the machine as well. so we can ask questions of the machine in simple ways without having to delve into the low-level hardware. Generally speaking, you won't look at that, but actually more close to where the users sit is an event-driven API. So this allows us to use the features of SpiNNaker without actually having to deal again with the hardware niggles, and that makes things a lot easier. So then we have our application code, which runs on top of that, and in our case, often is the neural network simulation code. If we then go to the Python side, on top of the Ethernet interface, we have a communication layer, and this basically allows you to communicate with the chip on the other side. And as I said, mostly with the monitor core, and which then allows you to access all the rest of the chip. We then have simulation control, which runs on top of this and does all things like it speaks to them. Having spoken to the machine and discovered what it looks like, we can then map a problem onto the machine, control the execution, and do data input and output from the machine, so we can load problems onto the machine, let them execute, and then get back results. And then running on top of this is usually the front-end interface. So this is things like Pine, which is the language we use for communicating. That's basically your neural network described in one language, which then goes through this process to get onto the machine. We also support some live interaction with the machine as well. So the front-end interface can sort of speak straight to the communication layer and then speak to the machine. As I said, that can speak over Ethernet, but there are other ways of communicating as well. So to have a look at how the chip neural network software actually maps onto the machine, this is our SpiNNaker chip diagram again, without so many labels on it. So our instruction memory is loaded up with that low-level API, some event-driven API, and the application code. They're all sort of loaded there into that instruction memory. So it's small, but we managed to squeeze in that amount of code onto it. We've done a bit of work to try and work out what we can put on there, and that's what we're able to fit now. The data memory is then used to store the neuron state during the execution. And it also stores what we call spike SDRAM lookup tables. So it doesn't store the actual synapses themselves, just a lookup table so we know where to find those synapses when we receive a spike. The ARM processor then handles events. So basically when something happens, I'll go into the details of the events later, this is, processor is woken up, does some work, and then goes back to sleep. This is things like neuron state updating and the processing of spikes themselves. The SDRAM then, as I hinted at earlier, is where we actually store the synaptic states. So we store the actual data in the synapses. So when a spike comes in, we have to go into the SDRAM, look up the information we need, and do the processing that way. But we also hold recorded data in the SDRAM as well. So if you're recording spikes or neuron voltages, you have to go into the SDRAM to write those down because there just isn't enough space in the local data memory. The DMA controller then does the actual transferring of synapses from and to SDRAM from the data memory. And finally, the router is then used to send spikes and receive spikes from their respective places. So when we send a spike, we send it to the router, it goes off and routes it to the appropriate places. And similarly, you might receive a spike there, wakes up the processor to do some spike processing. So what sort of events do we receive that the processor has to deal with? Well, as I mentioned, we're going to receive some spikes, and this is done by receiving a multicast packet. At this point, the processor wakes up, looks up the spike, starts some synapse DMA reading. When that read is complete, you get another event coming in. This causes it to do some synapse processing, which might be updating plastic synapses, processing any synapses on there, accumulating weights so that we can do neuron state update in a minute. And also, if you've done some plasticity, you might also do some writing back. So you start another DMA, which then transfers that memory you've changed back into the SDRAM for later use. And also, when a timer goes off, we then take the weights that we've calculated from the spike processing, update the neuron states, then spikes, and also we might do some structural plasticity, which has been introduced fairly recently into the code. We have also been investigating splitting up some of this processing between the different processors on the machine. So we can split spike processing from the neuron processing. In this case, we have to use that SDRAM because we haven't got the space, we haven't got any mechanism to communicate between the cores otherwise. So we write the accumulated weight into the SD-RAM, and then on the neuron cores, we can read that information back and start doing the neuron processing. This can be a bit faster to do than using the router itself, and also the routers are designed to carry packets of the size of spikes, so they don't necessarily have enough space to store accumulated weights as well. So in the software, we actually have mechanisms which work with the weight, with the delays of the system. So whenever a spike is received on SpiNNaker, whenever a spike is sent, it's essentially instantaneous. It crosses the network very quickly and we receive it at the receiving end. But of course, in neural networks, we want to have delays. So we have mechanisms for coping with this. And the way we do this is we have delay buffers. So what happens is if a synapse comes in, a spike comes in for a synapse and it has a delay, say of 3, we look in the third slot away from where we are and we write down the weight into that slot. If we then get a different spike with say a delay of 5 and a weight of 2, we put it in a slot further along. Now, if we get another delay of 3 and we've still not processed this yet, we actually update the synapse. So we add that on. So we're accumulating weights over time. And we're allowed to do this because the synapse models are linear that we're dealing with most of the time here. And if they're not linear, we have to have more delay buffers to separate out linear parts to do this composition. Now, the current buffers on our software allow us to support up to 16 delays in this way. But if we want to cope with very large delays, like a delay of 36, we can also do this with delay extensions which run outside of the main neuron cores. So for example, here the delay extension works in units of 16, and the final core then takes the final 4 bits of delay from this particular 36. So we put it through a delay of 32. It then comes into the core with a delay of 4 and puts the weight in the appropriate slot at that point. So it will have been pre-delayed before it arrives at the core. So this is not as instantaneous. It gets held up in some processor earlier on. And the reason these delay processors can cope with just 16 slots groups is because it allows the processing to be easier, whereas the final core has to cope with the actual sub delays of 16, and you just don't have space to cope with both of them. So this allows us to do both things. So we can also, as I was mentioning before, we can map our software in various different ways. The standard way we've been doing it for a fair amount of time is to put our neuron and synapses all on a single core. We can then add things like Poisson processing. So if you've got a Poisson source and you want to generate some input into your network, you can have this, and this will run on a separate core. We can also have, whoops, the wrong way. We can also add delay extensions, which I've mentioned previously. These also run on a separate core. We have been experimenting, however, with a split synapse model. Again, I mentioned before, and basically this splits into multiple synapse cores, which means you can handle different incoming numbers of synapses without impacting on the real-time operation of the network. This actually allows us to then get rid of the delay extensions, and we can actually deal with the delays, bigger delays, more than 16 on the synapse cores, because we have more memory now. We're not holding the neuron states, so we can do that in a better way. And this is what allowed us to run the microcortical column, the cortical microcircuit model in real time in the paper that was mentioned previously. We can basically split up that processing in so that we target different cores with different neurons as well, so different source neurons. And this allows us then to grow in an even more, allows us to run larger and larger network models without impacting too much on the processing. So basically, when we're talking about that low-level processing that goes on the machine, we'll now talk about the next layer up. So the next layer up is responsible for getting the neural network onto the machine. So basically, given a description of a neural network which describes populations and projections, we basically split up that network into cores. So we say, okay, there's some part of this population is going to run on some core over here. And we break that down across the various cores on the machine. I've shown you a single chip here, but of course you can split populations over multiple chips. And and it basically decides on what other components might fit on there as well, of course. So it may decide to put these, as I said, put populations on different chips. It may decide to actually mix the populations on different chips. You could have multiple parts of the same population on the same chip. It's all been split out. So once you've decided that, you then have to decide how you're going to route between the cores. So basically, how you're going to send the traffic across these chips, because the chips only talk to their adjacent neighbors. You have to work out how to pass them around. So you might send the data around like a bit like this. Once you've decided where everything goes, you then have to load the network onto the machine. So if we've got our projection and population like this, these all generate a reasonable amount of data that we then have to load into the machine, which can be quite significant. The largest part of any data that we have is usually the synaptic data, which is why we have to store it in SD-RAM, of course. In the cortical microcircuit simulation, the original way we did it, it took us 1.5 hours to generate the data. And then it took us 8 hours to load that data onto the machine. So of course that's not a very useful thing. It doesn't help us to run the neural networks in that way. People aren't going to be overly happy with that. So what we decided to do is we've changed the software now so it actually just writes down the descriptions of the connections, especially if they're statistically described. If you've got the actual literal set of connections to send up to the machine, of course you have to send them up. But if you've got a statistically described connection, you can actually just describe that to the machine itself and allow the machine to then do the expansion. In this case, then it took us 1.5 minutes to do that generation and only 1 minute then to load the data onto the machine. It's important to note that it then did take us 3.5 minutes to do the synaptic generation. And the reason for that is because we were able to do it in parallel. So we didn't have to take as long as the 1.5 hours to do the individual connections on the host machine, whereas we can actually use the parallel part of SpiNNaker to do that generation as well. And it's still 5 minutes is the total load time then, down from 9.5 hours. That's pretty impressive improvement in the software. SpiNNaker does allow simulation to run in real time. That's the whole aim of SpiNNaker. But if you have to, for reasons of complexity, you can actually slow down the simulation with respect to real time. So if we, for example, we are talking about these split synapse and neuron models, which help you run in real time. But if your network is just so complex, it can't even cope with those, or you're running the bog standard neural network software, which is the most easily accessed at this point, you may have to slow down your simulation. And we can do that because the simulation is in software essentially. So we can slow down all the cores by a fixed amount and run the simulation that way if necessary. So you can then get very large simulations on potentially smaller machines as well. SpiNNaker does support live interaction with the outside world, and things like robots can be connected to the board, and we can describe these connections then in the software and allow the software to set up everything so that the robot can be communicated with. We support interaction via the various inputs that I talked about previously, which you can do directly, but we also support direct connections over Ethernet as well. So if you haven't got complex hardware to plug in, you can do this with Ethernet as well. So it's not too bad. And then you use some software software in the middle which deals with this. So you can see here we've got a live spike connection. We can also transmit a new Poisson rate. So if you've got Poisson sources on the board, you can upload those live as the simulation is running. And you can also transmit out of the machine membrane voltages. So if you've got neuron membranes, you can transmit those out. And those could be used for things like motor speeds. So you can set it up that you're using the membrane voltage as a speed for a motor. And if you set up the parameters of the neuron correctly, that can work quite well. Okay, so how can you access SpiNNaker using this software? You can connect through the EBRAINS portal, the Human Brain Project portal, basically through the collaboratory, and we're upgrading that to the collaboratory version 2. Basically, you can submit jobs for batch processing on the SpiNNaker machine. I mentioned there's some servers in our machine room that sit next to the machine here, and they handle this remote SpiNNaker batch processing. We've also got a Jupyter notebook system running, and this allows you to do quicker experimentations and tutorials. So the tutorial stuff we'll be doing later will be done on the Jupyter notebooks because it's much more interactive. You don't have to sit there and wait for it to finish, and it's not restricted in terms of numbers of users simultaneously. There's a little bit of restriction, of course, because it's all running on the server, but I imagine it will cope with the number of people here. Okay, so that's the platform in general. I'll now show you some examples of things that we've done with the platform in the past. So I've mentioned the cortical microcircuit model, and basically the idea of this was to run it in real time on SpiNNaker, and this now has happened. There's a paper about it that describes how this was achieved. And we've also shown that this ran networks with similar results to a nest simulation. So we did some fairly complex statistical analysis to show that the output was basically the same, which meant that we're sort of validating that SpiNNaker is doing the right thing, because of course the software is different. So it's not just Nest on a SpiNNaker machine. We've had to do our own software implementation. We've also been working on a cerebellum model. This is still work in progress. There's paper in progress about the way we're dealing with this. It's similar number of neurons to the cortical microcircuit. Actually, it's slightly more, but not by many. The difference is that they're distributed quite significantly differently here. So the microcortical column was quite evenly balanced across the whole network, whereas the cerebellum model is actually quite lumpy. So you've got bits where you've got lots and lots of neurons, bits where you've got very few. This tends to lead then to having high synapse counts on the neurons. So for example, you get something like 30,000 synapses coming into these neurons here, which is quite high compared to the cortical column. The cortical column was quite high, but compared to what we expected, but this is on a different level again. And there's also quite a lot of spikes potentially coming in there. So and it's running at 0.1 millisecond time steps. So we have a lot of spikes to deal with all at once. Now, of course, we've got the system to deal with this. We just need to make the software do it. So splitting up the software into the neuron and synapse models is going to be necessary here. But we're talking about possibly having multiple synapse chips, never mind synapse cores. So that's going to create some interesting new parts of the software. But that is work in progress at this point. We've also had some students taking advantage of the ability of SpiNNaker to run other applications. So you can run neural networks, but of course there are standard ARM cores here, so you can run different things if you want to. One of the examples of this was an ear model known as SpiNNaker, just for the fun of the naming. And the idea of this was to actually model the physiological parts of the ear on the machine. So you could essentially receive sound input, and by receive I mean you might have had sound files which you can convert into seemingly sound waves on the system, feed those into the model, and then it can produce spikes. The advantage of this being actually running on the SpiNNaker platform is you can also then run your neural network on SpiNNaker as well and make these two things interact directly. So you're not having to connect this to multiple systems. You actually got your ear and your neural network all running on the platform. So that was a student has sort of played with that a bit. I don't know if they did. Most of it was about getting the ear model working, so I don't think there was a heavily amount of interaction with the network. But of course, it gives you that ability now. In a similar way, we've also played about with retina input, and a student has worked on biological representations of retina input on SpiNNaker. I think that same student was using a webcam at one point and converting that into a spiking camera as well. So of course, the idea of this is that you deal with spikes rather than light levels, and the spikes are produced from changing light levels, but you also want to potentially connect parts of the retina that are close together in clever ways that the biology shows us works. So you have photoreceptors connecting to the back-end network, but not just a single photoreceptor connecting to a single neuron, but connecting in a more complex way. I think they use this network to then show that you could do better machine learning tasks such as MNIST by doing this with biological networks. So that same work actually used structural plasticity to produce good results with MNIST. And you can sort of see here how our structural plasticity basically rearranges, but this is with purely structural plastic connections. You can sort of feed in figures into the network, and it can map various numbers. So if you give it a certain example of zeros, lots of different zeros, you can feed it in, and it will create the right connections to then sort of represent zeros. And then when you feed in, it's gone backwards again. When you feed in the numbers, it can then work out which of these systems is actually activated. So which of these neural networks is showing the right result. And you do this with a sort of offline winner takes all scenario, and then you can do MNIST a bit better with spiking networks. And yeah, this showed that we did quite well with just structural plasticity, which is quite interesting. But of course, it was again running on SpiNNaker in real time, which was the important part here. Again, with the structural plasticity, we've been able to do some motion detection. So basically, where you've got lines moving across the screen and you want to tell which direction they're moving in, and you can use the network similar like this. At the bottom here, you can sort of see how the network performs. The diagram on the left here is a diagram with delays, and the diagram on the right is without delays. So the delays are all static, essentially, on the right diagram. And this shows that it's quite important to have these delays in the network. And of course, in the network with motion, this does make a lot of sense because things are moving through time. So having delays to be able to line things up makes a lot of sense. But this sort of shows some power of spiking neural networks where delays could be quite important. Some other work, you may have heard of SpiNNaker being used to do Sudoku solving. Basically, we set up what's mostly an inhibitory network on SpiNNaker here. So you, if you think of Sudoku, it says when you've got a certain number in a cell, you're not allowed to have the number in other positions in the puzzle. And so you can inhibit, you can basically set it up so it inhibits when you've got a certain layer, it inhibits all the other ones from having that same number. So here you can sort of see that the 7 stops all the other bits in the same row and column as being a 7, and then the same Sudoku square. You then have to add in some excitation, some random noise in the background to make this actually do anything, because of course it's all inhibitory otherwise. So it was interesting to sort of see how much excitation, random noise you added into the network to then make it really do the solutions. Backwards in my own slides. And here you can sort of see a live output from one of these networks running, where it may not come through very well in Zoom, but basically you're sort of seeing it trying to solve the network. Even though it gets to a steady state, there's nothing in the network that actually tells it that it's in that steady state, so it doesn't know it's finished. So of course you have to sort of read this out at the point where it's reached a solution, and it might actually, the random noise might knock it out of that solution, and it might start trying to solve the problem again, or try and solve a different problem. In fact, every now and again it can cheat as well, because it's sometimes if your fixed number levels are not high enough, then because they're also produced by essentially a stronger level of background noise, but if that noise isn't high enough, it can actually be overridden by the other parts, so then the game starts to cheat, which is quite interesting. I think that was interesting when you don't set any numbers, you can let it dream a puzzle as well. So it can basically come up with a solution to a puzzle you didn't set it at all. Quite interesting. The other thing we can, similar to the SpiNNaker problem, we can actually run other virtual environments on the machine as well. So here we've got an example of Breakout running on the machine. You can run that alongside the neural network, of course, again, and have them interact with each other. So you can have a sort of reasonably fast interaction with a virtual environment here, which is quite a useful feature of the platform. We've also had people in our Jupyter environment using other things that connect from the outside world. So people use it. There was a case of a user using OpenAI Gym to do something. In this case, this is the Space Invaders. I don't think they actually use Space Invaders. This is just one that I've managed to get working quite well. And basically, you can interact then with the neural network and train the neural network potentially so it can win the game better. Of course, because the software supports this interaction over Ethernet, this allows you to connect with really any environment externally if you want to. We've also had a lot of interaction with the virtual neurorobotics environment, and quite recently it's been updated so that you can interact with SpiNNaker This is all working on the Jupyter platform now, so and it is listed in the tutorial this afternoon, although I don't feel there will be a lot of time to go into it, but it is there if people want to play with it. This basically lets you have co-simulation, so you can have the large brain model running on SpiNNaker and the robotics environment running elsewhere, which is actually just running on a host computer next to SpiNNaker. You can see here, this is a Husky robot. When it sees red, it goes towards it. This is just our sort of preliminary example, so it uses a very simple neural network, in fact, but you can make more complex networks, of course, as you wish. We've also done quite a lot of work with real robotics devices. We've got quite a lot of support for the pushbot robot, which you can see in this sort of corner, bottom right corner here, sort of following a light. Basically, you can set up various networks with that, but the software's set up so that it's really easy to plug in a pushbot, but actually it's quite easy to plug in other robots as well. So to that end, we've been actually working with the iCub robot with the IIT to produce a cerebellum network that will allow some amount of gaze tracking. So basically, as you move something around in front of the robot, it can work out where to position the head and the eyes at the same time. Quite interesting. The SpiNNaker machine can also support non-neural applications again. So someone's actually, again with the iCub, did something called a particle filter. And basically this allows the processing to work out where certain things are in the scene to be worked out, but using the parallel nature of SpiNNaker to be able to speed up this process, so you can, and to be able to track more particles essentially. So you can see in the graph here that with SpiNNaker they were able to track more particles with a shorter update period. So that was very useful, especially for tracking objects with the iCub again. In a completely different field, we've also looked at MCMC on SpiNNaker. Basically, the idea here is that you have so many cores that you can just start lots of them from a different starting point, and then produce many more samples than you would be able to do on a single host machine. So you start all these off in a different place, and they all go to different, find different samplings, and then you can form them back on the host machine again. Okay, so to look forward to the future, what is there in stock? Some developments in progress. We're working on the SpiNNaker II chip, and there is a JIB1 test chip, and there's a JIB2 test chip that's very close to being available now. It's ready, it just needs some the board put together so that we can play with it. So the JIB1 test chip is part of the SpiNNaker II development. It just has a couple of what's called quad Ps, so it has 8 processing elements on it, 8 ARM processors with memory and associated parts. It has a SpiNNaker router, and it has a couple of links, and it has a dummy SD-RAM, so it doesn't really have any SD-RAM. It just has a little bit of memory plugged onto the side so that we can play with it a bit. The idea of SpiNNaker II is actually to make an 152 core machine though, and the idea is that it will be very similar. I think we, with the SD-RAM, we haven't quite managed to keep it to 1 watt per chip, but it's still quite low watt. I think without the SD-RAM it's 1 watt, and then the SD-RAM has more power this time. But it's got some extra features as well, things like exponential calculations done in hardware, and some other features that allow us to speed up the processing, some better ways of speaking between the cores as well, so there'll be more inter-core communication on the chip. We'll still have the 6 links of the existing architecture, so actually the system from the outside, from the software side, other than having more cores, will look quite similar. From the low-level software side, we'll be able to do more, but from the high-level software, hopefully we'll be able to do very much the same as we were before. So we can use this same software, and we're going to look at developing the software for this. In particular, of course, we're going to have to change the low-level API a bit to take advantage of those new features. And this in turn means that the chip monitor will have to change a little bit. We're expecting the boot process to be a bit different, but we'll have to do that. Basically, we're hoping that things like the event-driven API will mostly stay the same. It has to be extended a little bit so that we can add in new features, but actually a lot of the main part of the code will stay the same. And then on the host side, of course, the communication will have to change a bit. because the communication model is different from SpiNNaker 1. And the mapping will need a little bit of change just because we have to take account of those more cores per chips. But hopefully the front end interface won't have to change much at all. So that's the idea. So a lot of the software will hopefully then be, you'll have to recompile things, but then it will just run on the SpiNNaker II platform. So are there any questions?